I guess the job here is to kind of sum up the workshop, and so since neither Chris nor I have any conclusions personally, we thought we would have some of the participants give conclusions, particularly some of the people who haven't spoken at the workshop. So to kick things off, I sort of identified, we've seen a whole bunch of different paradoxes based on Wigner's friend, different sets of assumptions, but I've identified, I think, 4 things that came up in the workshop that people have been talking about as possibly relevant to the resolution of these paradoxes. So let me just talk through these 4 things, and then the panelists can say what they think about the relative importance of these for resolving the paradoxes that we've heard about. So firstly, yesterday, I think it was at the end of the meeting yesterday, Chris came up to me and he said, well, it's obvious, everybody is conflating probability 1 with certainty. That's the problem.
Probability 1 with truth.
Probability 1 with truth. Okay, certainty with truth. Okay, so we can ask whether that's one of the most important things in resolving these paradoxes. The second one is consistency. This is Renato's assumption C, right? So the idea that if you know that Alice believes X, then you should believe X, right? So should we take on board other people's predictions as our own, basically? There's the problem of self-reference, which is it legitimate to apply quantum theory to yourself, right? So in some Copenhagenish interpretations, we would just say, never apply quantum theory to yourself under any circumstances. So is that the resolution? And then the fourth one isn't really proposed as a resolution to like the main paradox, but it has come up in a couple of talks, whether the very fact that you're describing a measurement interaction that Alice is making unitarily somehow means that Alice is devoid of free will, because you're describing her by a fixed unitary interaction. So maybe if the whole universe evolves according to unitary dynamics, there's just no free will ever. So these are the questions, these are the issues, these are the ones I've identified anyway. So I'd like to hear from the panel whether you think any of these are important or whether you think it's something else. So maybe we'll go, everybody can talk for like a minute or so, and then we'll open things up. So since Jack is still eating, we'll go from that end.
I should have taken a cookie. Yeah, well, maybe I want to comment on a general point on Wigner's friend in general, namely, so I think it would be nice, even though these in principle arguments are important and maybe interesting, to just keep in mind what something like the standard picture of measurement that we have in quantum mechanics, which is that if you have a reasonably large macroscopic measuring device which produces fixed outcomes, and fixed in the sense that you could sort of process them, store them, and do whatever on paper and whatnot, then the standard account here is that a collapse has effectively happened. Right? No matter whether I describe that unitarily or in whatever, I mean, yeah, unitarily in the sense of quantum mechanics, but collapse has effectively happened in the sense that the correlations that I would need to reverse the process, for example, are sort of have been lost in a macroscopic system and they cannot be retrieved. Right? Now this would happen also inside a box. Right? So if we say that the friend in the box has made a measurement, there is an element of irreversibility in this maybe only practical sense, but very real sense, has already happened. So Wigner doesn't have much of a choice unless he is a super demon that somehow knows much more about Alice, for example, her detailed quantum state or something like that, that would allow him to just apply unitary evolution, maybe reverse it, and then think of something else to measure. So the Wigner here is a super demon that we've been talking about. Okay, so many here will say that that really is only a practical problem. So we want logical consistency problems solved and stuff like that. So this is maybe not a relevant remark at all, but I think to me this is one of the messages in quantum information, that keeping track of these orders of magnitude of difficulty is a useful thing. So we are not just talking about something that is maybe cannot be done in the next couple of years, but we are talking about something that is unlikely to be done in the next trillion years, or maybe exponentially many ages of the universe. Right? So the scale of impossibility here is really staggering. If you think about a measurement, I mean, if you send your graduate student into the box and let him make the measurement, then the odds for reversing the poor guy are zero. Right? They're just zero. And I think this is something that should be kept in mind. I have nothing against, in principle, arguments. Well, I do, but but no. I mean, I think this has to be carried through. That's okay. But to keep this in mind, I think, is a very important aspect. Now, for certainty, we have. It's not just a question of probability 1 and truth being confounded, but probabilities very close to 1 are something that happens all the time, especially in discussions like this. For some things, there will be a very high probability. Also for consistency, if we have this standard account, then automatically this will be consistent. That's part of the definition of a measurement, that the stored results in the box make sense outside the box. So there's no problem there at all. Right? Applying quantum mechanics to yourself, well, this is partly also, I mean, for me this would begin with applying quantum mechanics to a cat. That's a problem of a similar order of magnitude. Just writing down a wave function, calling it psi, says very little about cats. And, well, nothing actually. There's nothing of predictive value that we say this way. So I think the application of quantum mechanics to macroscopic systems is something we have to solve at a very fundamental level, and the practical level here is a relevant one, actually. So how do we actually justify the use of classical properties for macroscopic systems? If we understand that better, we will also be clearer about these orders of magnitude and stuff like that. So sorry, I didn't quite stick to your scheme, but
it's all right. Yeah,
I thought this was a.
It's just I just put those up in case somebody doesn't have anything that they want to say. Veronica, do you want to?
Yeah. Okay, I actually agree there to a very, very large extent, but would rather view these Wigner's friend type experiments like from a different direction. So I would not be interested in, sending myself or maybe Czaslaw into superposition, but rather, thinking about what type of system, small systems would still meet requirements that I would attribute at least some degree of agency, or, for example, can they make this computation that would lead to the prediction in coherent superposition? Is this possible? These like more observer-like systems, and then see whether by that I can actually establish what we call an actual contradiction via an output, and see, okay, so this might not be an observer in the sense like it might not even be a supermacroscopic object, something in between that is sufficiently complex to do something that I would attribute some sort of agency to it. And then I have a Wigner's friend type situation.
Yes.
So that, yes. That was actually my main point. About consistency. Regarding to what I said, referring to what I said before, I think I would say like a state update rule or an entangling unitary are just two different formalisms for me to describe a measurement. And if I, in one setup, like a Wigner's friend type setup, apply them, I would say inconsistently, like to one measurement, like one agent applies this formal description, the other one applies the other, then I think I cannot require consistency in the predictions. would be my like. I'd say okay, you can use a subjective collapse model, but then I think it makes no sense to require consistency in such Wigner's friend type situations. Self-reference. I don't have a big problem with it, to be honest.
Clearly, from your talk.
And free will. Well, given that for the situation I have in mind, like Wigner's friend-like experiments, I'm not talking about human or some thinking, very complex entity. For me, this free will consideration is not too relevant, actually.
Okay. Matt?
Okay, so on certainty, we've heard that like probability 1 is just another probability assignment. I mean, I think there is a difference between saying that I assign probability 1 to E and probability 1 to not E, versus saying I assign probability half to E and I assign probability half to not E. And I think that difference was all that was important for the single world assumption. So it's a bit more, there's a bit more going on in the consistency assumption. In the consistency assumption, like probability 1 does seem to be playing a big role. So I think if you don't think probability 1 is special, then there should be a version of it that applies to arbitrary probabilities. So like, what should I say if I'm 99% sure that Alice is 99% sure of something? I haven't seen that. With self-reference, I think it's useful if you haven't done it to look at what goes on with the original Wigner's thought experiment in Speck toy theory, because it's kind of a nice example of how self-reference changes things a little bit, but there's still a very consistent story of what's going on. Obviously that doesn't apply to these more complicated things that aren't in the toy theory. And if you're worried about free will, you just haven't read enough Dan Dennett. So. Daniel Dennett.
If we were having that discussion, I would come back at that topic.
Like so once you've read enough of that, you'll realise there's no inconsistency between thinking people have free will and that you can describe them with a unitary.
Well, I might start off just with a comment on that I thought a nice ingredient that is added by game theory considerations is that I think it shows exactly that there isn't necessarily a contradiction, because in a game we're accustomed to, on the one hand, believing that our opponents have free will, but at the same time modeling them as if they're following some strategy which we can use to predict their actions. And we can do that consistently just because that we believe that they have certain goals or utilities that they're trying to attain. So I think it might be fruitful if people want to undo confusions about the role of free will here, to think about utility functions and game theory. I also wanted to comment a bit on what Reinhard was saying, because I do think that it's kind of like, since you just said that, it occurred to me that it's funny that like two of the kind of axioms that you proposed everyone should presumably agree on were, one was kind of being broadly empiricist, and the other was having this idea of the universality of quantum theory. But at face value, it seems a bit strange to say, well, I believe I could, in principle, apply quantum theory to a cat, and yet no one's ever done that in an experiment, and we have very little prospect of doing so. So I think that universality assumption, I think it does make sense, but not necessarily just for the reasons of raising the question, why are we justified in using the macroscopic variables that we measure But I think there's a deeper aspect to that, which is that in adopting this universality assumption, we're not saying that we necessarily believe that we could do such experiments on cats and people. It's that we're exploring the nature of quantum theory and its limits. So we're hoping, on one hand, to find out how it would break down if in fact it breaks down at some point. And we're also trying to learn, why is quantum theory true? I think that everyone who identifies as Copenhagenish is probably a little bit unsatisfied with why the world is quantum. And by trying to elaborate some of its most extreme consequences, we're hoping to answer that. To find what was the Wheelerian...
The quantum principle.
Yeah, what's the quantum principle?
Could I maybe comment on the universality of quantum mechanics? So definitely, well, there are two answers to this, right? One, two obvious answers. One, it's obviously true, and the other is obviously false, right? So we have to be very careful what we actually mean by that. So on one level, nobody doubts that macroscopic objects are made out of atoms, and these are appropriately described by quantum mechanics, and the composition is also described by quantum mechanics. So we can write down a many-body Hamiltonian, and nobody has any doubt that this is a relevant part of the explanation of whatever we want to explain about a table or so. Right? On the other hand, just saying that produces something which is not a theory. It has zero predictive value. We can write down a psi and write down the Hamiltonian with n equals 10 to the 23 or something, right? So this is sort of looks like a well-defined mathematical object, but it's utterly and totally useless just as such, right? So it requires an active piece of work to actually get to a level where we can make predictions in a relevant way, and this is what it makes a theory, right? So a good theory would allow us to maybe take some, I guess the term for that would be coarse graining, right? So we have a rough description of the macroscopic body that doesn't look at every detail, but is a sort of on a macroscopic level, good enough. And the research program here is to do this in such a way that what we get has predictive value. So that if we have coarse-grained information, we can predict what happens at a later time on that coarse-grained level. It's not at all trivial that this works. Apparently it does, or it must somehow. And there's a lot of theoretical work to be done at that level. So the correct theory, we should always use the best theory available for, let's say, a table. And this best theory available for a table, if we want to learn something about tables, is absolutely not quantum mechanics. In that sense, it's very clear that quantum mechanics is simply not the right thing to learn something about tables or cats or humans or measurement. Right? So in that sense, obviously yes and obviously no, but we should be aware that there's a lot of honest theoretical work that still has to be done there to do this at a level of generality which would be satisfactory. Right? There's a lot we would like to understand at a very general level. It's a very general question, so it deserves a general answer, and we don't really have that. So a lot of the talk about effectively macroscopic systems is wishful thinking, right? Absolutely, and we should do something about that. This is clearly a job for the theoretician that we haven't done very well yet. Right? But on the other hand, I think every physicist would be convinced that something like that should be true. Right? It's just not very clear what form it will ultimately take. But in that sense, universality of quantum mechanics is nonsense. Right? It's simply not the right theory for macroscopic objects.
Well, I can't exactly say that I disagree, except that I do. I think I disagree with where you're taking this, because I think the point of I think universality is best thought of as something that we want to take as a postulate in our thought experiments in order to learn something purely about the theory. And in this sense, there's no need to try and imagine a real experiment that would correspond to these thought experiments. It's sufficient that within the scope of the theory, it's perhaps, how shall we put it, imaginatively plausible. A bit like, Einstein imagining looking into a mirror while traveling at the speed of light. I don't think he needed to worry about the feasibility of doing that experiment in order to derive useful conclusions from
Actually, it was
considering it.
running in parallel to a light ray at the speed of light. I think it was a...
I've heard different versions.
Okay,
of it,
also,
to be
he had some different things. Yeah.
Okay, so I want to open it up to the audience in a minute. Let me first issue a challenge to Reinhard, which is it really a trillion years? So I think Renato has made this comment in the past, which is, okay, this requires a few assumptions, but if you believe that we're going to build a scalable quantum computer, and if you believe that general artificial intelligence is possible and has agency, then in principle you can run this kind of experiment in an extremely controlled way with very large numbers of qubits on a quantum computer. Now, would you consider that an implementation of this kind of experiment?
Could well be. I mean, it's absolutely true that trying to build a quantum computer is exactly the uphill struggle against this general tendency towards equilibrium or microscopicity, right? So we're exactly combating that, right? In the attempt to build a quantum computer, and so once we do, and that is not really around the corner, but I mean not for this kind of purpose. Then yes, interesting things might happen, and what you mentioned, like reasonably large things that with some stretch of the imagination I could call agents might actually come up in this way. It's maybe hopefully better than what people call Schrödinger cats in quantum optics. This is very that's so different from a macroscopic object that it's a bit of a joke, right? So maybe something that is actually better than a joke and deserves being called an agent more than quantum optical Schrödinger cats. It's quite possible, yes. And then of course, yeah, then things are going to happen, and it's good to be ready for that moment, maybe.
Okay, I want to open things up to the audience. If you have a specific panel member whose the question is directed to, please mention it, or if you just want to direct it to the whole panel, please say that as well.
It's more about the comment of sharing the worry of whether these experiments is it a question of practical impossibility or something more? And in order to answer this, it will be important to understand which resources we need to really, for example, reverse a unitary. And if these resources turn out to be higher than what is available in our lab or in our universe, then this maybe points into something which is not only practical kind of impossibility, but pointing maybe into even some new physics that we right now don't understand, but we will say, well, I believe in quantum theory, but actually I cannot perform this, not because there is no resources, these measurements. So something is here incomplete, and it will be important to understand really what are the resources for that.
Does anyone want to comment on that?
Maybe only that this question of when has decoherence happened is especially in this gray area where we are sort of close to small scale quantum experiments and not quite yet in the fully macroscopic regime, then it's partly a matter of choice on the part of the theorist or the experimenter, whoever runs such a thing, to say, well, let us decide that we're not going to run after thermal photons that have escaped to the rest of the universe and trying to bring them back. Right? So this is a decision that we make, and there's a question of degree here, and in which I actually have a choice whether I want to describe something as decoherence has happened, and I trace out the thermal radiation that has escaped, or I don't. So I think in this intermediate area, it will be a question of choice. So it's not an absolute thing.
No, but I could imagine that maybe at some point you will see that it's even of all resources available within the universe
sure.
are not.
We're very, very quickly about what the universe has to offer. Very quickly.
Can I kind of interject that when you say it's about whether decoherence has happened, that makes it sound as if it's something that either has happened like for everybody or not, whereas it seems like a big point of
That's what I wanted to
this
say. That is,
Wigner's friend experiment is that you have one agent who thinks decoherence has happened and another one who thinks it hasn't. And so I think that the question, has decoherence happened, should be a little bit modified to make it relative, to say when has decoherence happened for some agent.
Like relative to resources or technological capability.
And-
or also by choice, right? I think we agree completely. Yeah.
I mean, I think Czeslav's point was that it could be that there's a certain degree of decoherence, a certain system size beyond which it's just physically impossible to reverse it because of energy resources or entropy resources or something requires more than exists in the observable universe or something like that. Something like that seems plausible to be in the everyday world. To me, it doesn't seem that plausible that if you're running this on a quantum computer, that would be the case, right? Because there everything's extremely controlled. But there certainly could be something like that.
Can I potentially propose a candidate for something that you might not be able to fight against?
Sure.
So, for example, let's assume that gravity or space-time is a quantum thing, and therefore it also causes decoherence, and you can't shield from gravity because, it's just space-time, right? And in some speculative models of quantum gravity that I'm testing in my lab, the size of the uncertainty is about an atometer at a 1 meter scale, so which is pretty big, right? And presumably if your quantum computer is 1 meter large and has normal mass of a 1 meter large object, you would quickly run into that problem, and then that would destroy all your causality axioms, and yeah.
Any further comments from the panel on this? Okay.
But it seems that this comment is ignoring fault tolerance and error correction, because even if we had a finite influence everywhere, we could, of course, by known techniques of fault tolerance, protect the logical degrees of freedom from that. And for the argument that
Actually,
you were mentioning that I'm usually making the only relevant thing are the logical degrees of freedom. So
I'm working on a calculation on that one.
Yeah.
Actually, yeah. So, yeah.
Yeah, so I wanted to shift a bit, if nobody else has a follow-up on this. On what I've mentioned briefly in a slide of my talk, the minimum requirement for an agent, something that it doesn't seem to have been spelled out completely during this workshop, but every one of us, we discussed several details, but apparently we have different sensitivity for what we mean by an agent. So there was yesterday, after Chazav's talk, this problem of the free will of an agent in science. If he doesn't have the freedom of choice to choose, for you for instance, so there was this problem that if he doesn't have the freedom of choice of turning the Stein-Gerlach apparatus, then this is not an agent.
If he doesn't have that freedom of choice, why does he have the freedom of choice of which update rule?
Right.
Choose.
Yeah, no, I'm not good.
So in some sense, I'm sorry to interrupt.
No.
But there's so much that is just left out of the discussion here. They act as if there's freedom for one thing, but not freedom for the other.
Well, and also,
whenever it's convenient for making a paradox.
Jeff made the point that sometimes it's the freedom of nature, it's not necessarily the...
Maybe I should clarify why I put that point 4 as a possible being involved possibly in the resolution. It's because if you think that describing something unitarily necessarily means that you don't have free will, and you think agents have free will, then the implication is you must never describe an agent according to unitary quantum mechanics. And if you never describe an agent according to unitary quantum mechanics, you don't get a paradox, because Wigner cannot describe Alice's.
You don't have universality.
They don't have universality.
It doesn't.
I can treat you with a unitary and not take away your free will as long as I don't say my unitary is telling you what to do. I can just be using that to model my expectations for what you do. See what I mean?
Yeah, of course.
And I never have to reject the universality of unitaries to say that.
So you're fine with this, that then your free will can be described, not controlled, but can be described.
You can have your cake and eat it too if you accept that unitaries are epistemic.
Yeah, if the unitary just encodes my beliefs about what's motivating you, what I think you're going to do next, and so on. I mean, if you kind of coarse grain that whole thing.
If it isn't steering you.
But then it should. Your response should not be now free will, because we agree on what you heard.
Okay.
Yeah.
There was an interesting discussion in the early days of quantum mechanics, right? So Pascal Jordan, I think, was one of those who said, now quantum mechanics has shown us that in contrast to Laplace's demon type of scenarios, man has free will. Right? So they actually made this connection, which is a bit ridiculous, because to have a unitary process determine what you do is not that much better than, and have a random process essentially determine what you're supposed to do, is not that much better than having Laplace's demon decide for you. So I think this was completely a red herring to see to see the randomness in quantum mechanics as a sign of free will. It never was, and was never relevant for this problem. But but quantum mechanics as a way to treat macroscopic systems, to bring that back in, I mean, there's always a huge lack of predictability there, and we don't. I mean, this opening is there anyway, and it's the same as it was in the 19th century.
It's actually worse than you said, because even before quantum mechanics, when people first discovered the idea of statistical irregularities in human populations, so the idea that the distribution of, say, suicides in a city obeyed a bell curve, people thought that this statistical evidence showed that people don't have free will, because there's sort of a quota of number of people that have to kill themselves each year. It can't be due to. So people originally, when they saw probabilistic predictions for human beings, assumed that was evidence against free will. And then when quantum mechanics came around, people said that having probabilistic predictions was evidence that there was free will. So it's basically the same evidence having two opposite conclusions. Are there any other comments, questions from the audience at this point?
Question. Matt said something which I think really brought one thing to the point, namely about certainty, that there should be a difference, of course, between making a if a theory makes a statement that it's certain that the outcome is 0, and the theory also makes a statement it's certain that the outcome is 1, in the sense of probability 1, then this is certainly different. This is less satisfactory. I mean, you didn't say it in these words, but this is less satisfactory than if the theory just says it's 50% certain that the outcome is 0 and 50% that the outcome is 1. Now, I would be interested, because you were always insisting on this meaning of certainty. What you would say, again, the argument that essentially the only thing we need really is to say we want to exclude the fact that the theory, so we are not happy with a theory that assigns probability to x equals 0 and at the same time assigns probability to x equal 1. I don't need even to have more, let's say, meanings to what is now true and so on. This is just two statements the theory makes, and if the theory makes both statements at the same time, then this seems unsatisfactory. And I would be interested in knowing from you what you would think about this, whether this is...
Well, I would think that's unsatisfactory, because probability of x and probability of not x should equal 1. So if I have, so it's still a contradiction. It's still a contradiction in a mathematical sense. But at least in early presentations of your paradox,
Yes.
I thought I could pinpoint spots where you made the transition from probability 1 to truth. And in Lydia's paper, actually, I found a spot where she transformed probability 1 into truth. And I have a qualm against that because that is a key assumption in the EPR criterion of reality, that if, without in any way disturbing a system, I can make a probability 1 statement, then it corresponds to an element of reality. And I've always wanted to block that, and there was an easy way to block it by recognizing probability 1 as a subjective statement. So I would be loath to give that up, and it seemed, at least in some of the presentations, this was crucial. But you have tried your best to get around that.
Do you think that this is really not essential in these arguments? That really this is the one that actually makes the whole paradoxical? I mean, do you think that, or it's just cleaning the language and...
No, Renato has been right about us rejecting consistency, for sure. It's when in the earliest presentations, I think I wrote Renato a very long email about how it was claimed that that there was a general framework for considering all interpretations of quantum theory, and if you're a single world interpretation, then you must violate at least one of these desiderata. And the long note that I wrote to Renato was that his notion of theory just didn't capture nearly any aspect, or let me be more forceful, didn't capture any aspect whatsoever of cubism. So we violated your notion of certainty, we violated your notion of consistency, we violated your notion of a theory, because a theory was a story of the world rather than a description of how agents should best adjust their decision making. Things like that. So
I perfectly agree with that. So maybe the question is rather about the new formulations which arose from discussions, and let's say the way it's presented now, usually whether there you would say now you can really say the thing that remains that is violated by cubism is just assumption C, and the others are now well covered or fit into cubism. Is that now the case? That's maybe.
I don't understand it well enough to know whether I would accept that. I think that is Rudiger's feeling. That it's that in the reformulation.
Yes.
Well, no, there's also the self-reference. So he accuses all of you of.
No, I don't think he accuses Renato of it anymore.
I think made it very explicit.
I think it's just C now, but I'm not 100% sure either. But I do think that C is the main issue. I think.
Okay.
I think I would like to propose the universal law of cubism, which is that whenever one proposes a framework for physical theories, cubism will necessarily lie outside of it.
That's been the goal always.
Anybody on the panel want to comment on any of the discussion so far?
I actually have a question
Okay.
about cubism. Because
I'm not on the panel.
Try now.
close enough, close enough. Because sometimes I get the impression, but I'm not sure whether I'm correct there, that cubism to some extent always says I could always just be wrong in my prediction. Is this part of the theory? Because in that case, this is a subjective degree of belief. I calculate something and say, yeah, this is my expectation. I would bet based on that. And then something completely different happens, and you don't. Sometimes I think you say this is still fine.
Well, it happens all the time.
Yeah.
People make
Yes.
bad decisions based
Yes.
on
No, but I mean,
probability.
no, my point.
Nearly one assignments.
Okay.
I'll give you a good example.
Example, there were, how many terrorists were in the flights that went into the World Trade
7.
Center? There were 7?
I think there was.
Yes, because they had the strong assumption that they would be rewarded with 72 virgins in...
I think it's 40, but okay.
Oh, okay. So they effectively made a probability one statement in the sense of decision theory that they gambled their life
Yes. No. My question there is.
for something, and at least I would be willing to bet that they were not rewarded in the way that
How would you know?
I think I can kind of say in a sentence that I think cubism is not supposed to tell us what happens. It's supposed to tell us how we should deal with what happens.
Yes. No, but my question is.
But in principle, anything could happen.
Yeah. No, but you have this. I mean, you use this for quantum theory. So you say you have a means to calculate, and based on these calculations, you would bet, right? Like born rule wise, you get this problem. Yeah. Okay. At which is there a point where you would say, like, calculating this way and being unsuccessful, I would actually start to revise my theory, like my ways to calculate. Does this ever happen for cubism? Because sometimes I have the feeling it never does.
Put slightly differently, how do you falsify?
Thank you.
cubism?
Yes.
So that was more or less what you
yes,
said.
exactly.
What if quantum theory is not true? Suddenly there are some data not fitting with quantum theory. What would you do?
So if someone in their laboratory is able to clone an unknown quantum state, I would say immediately cubism is invalidated.
What is unknown state? How can you be sure it is unknown state?
If quantum evolutions weren't linear, if there were evidence of nonlinearity in
You
evolution.
use now terms, mathematical terms. I'm not sure what it means in the lab.
I'm simply saying it has been tailor-made for what quantum theory is. And if quantum theory were different, if something falsifies quantum theory, then it would falsify cubism.
But what would you
rather
do is
easily.
with quantum Bayesianism? Would you adapt the method, or you adapt somehow quantum theory, which you don't think it's a part of Bayesian method? Well, what do you adapt then, from your point of view?
What would I adapt?
Because this is what is happening in the Wigner. You have to adapt this state, update law, something else.
The historical progression was taking quantum theory as given and trying to understand it. And then slowly feeling compelled into a more and more subjective Bayesianism. So I offer this, at least this historical record, which you can read in 2,349 pages on QuantPH. I offer this as evidence that if quantum theory were different, I wouldn't have ended up in this position. Consequently, if we found evidence against quantum theory as it presently stands, for instance, we find nonlinear terms in evolution of quantum states, then I would abandon cubism. I would say the experimental evidence seems to, after all, indicate that quantum states are ontic, not epistemic.
Well, why ontic? What if it's just slightly more than 2 square root of 2? Still, while it's Bell inequality, but it's not quantum theory.
I explicitly said nonlinearity in evolution.
But would you?
But if it were another general probabilistic theory, it would depend upon whether the general probabilistic theory has a number of the features that compel me to think that measurement outcomes are personal to the agent. So for instance, if it were a general probabilistic theory that somehow did not have Cauchy-Specker style violations, then I would not go so far as cubism. If if it never had a Bell inequality violation. So a general probability, if it were like Speckin's toy model, and it allowed for the possibility of the states of knowledge or states of belief being about ontic variables, then one would not need to go so far
I
as
agree.
saying...
But what if it is not the case? Just the opposite. It has all features, non-classical features, is quantum, and it's not.
And it violates the Ransom bound.
Yeah.
Yeah.
What would you?
So it's embedded in a.
How would you call this? Is it now still quantum Bayesianism, or it's not? It's another type of Bayesianism, and if it's so, what is then so quantum specifically in the quantum?
But can I just point out that there's seem to be two aspects of cubism that are maybe being conflated or mixed up here, because one is the subjective Bayesian approach to science, which itself transcends quantum theory and could be applied to Newtonian mechanics if you want to. Where you try to think about physical laws as describing, normative rules for making good bets about measurements. And then there's the laws themselves, which Cubism says are those normative rules based on the evidence that we do have, one of which is the Born rule expressed in the Cubist form. And these two things are different aspects. You could revise the Born rule and replace it with some other rule based on the evidence without giving up the subjective Bayesian approach to doing science. So which of these are...
So the aspiration of quantum Bayesian is not then to derive the Born rule, because this is just our experience that we have used, that this matches some predictions, or it is an aspiration, because it seems like it's not.
I don't believe the Cubists tried to derive the Born rule. At least, mostly I see it taken as an axiom, right?
The reconstruction game we've been trying, not nearly so successful as anyone else's reconstruction game, is an attempt to take the Born rule, suitably expressed purely in terms of probabilities and no quantum states, as the fundamental assumption, the fundamental empirically recognized fact, and then reconstruct all of the rest of quantum theory from it. So positive operators and unitary evolutions. The Born rule is not obviously enough to imply that, but maybe it already forces some of these features on you. But your original question was, if we had a generalized probabilistic theory that was not exactly quantum theory, if it shared the main features of quantum theory in the sense of no-go theorems like Bell inequality violations, no-go theorems actually like the PBR theorem, which I've always viewed as actually evidence in favor of cubism, because it says if you want to have if you want your epistemic states to be epistemic about ontic variables, then that's inconsistent. The epistemic states are actually ontic after all. I've always viewed that as evidence in favor of an interpretation. So if you have a general probabilistic theory that has all of the same, or many of the same no-go results, then I would say, yeah, we should probably interpret it in the same way. The actual rules, like the Born rule, will now have to be modified in some form. And maybe we don't get exactly the positive semi-definite operators back. Now we get a general class of Hermitian operators in some representation.
What would convince you to modify? So what is the evidence that you're talking about?
The problem is that the Born rule is an axiom, and I think that's exactly where we get this question. Once it's an axiom, you can never revise it, because whenever you would get a result which is not in accordance with the axiom, you would say, the state preparation
you would
was
revise it if the axiom looks like it was a bad move.
No, but
you choose a different axiom.
Your point is, whenever the outcome would not be correct, then the state preparation would be wrong, because as Rüdiger always stresses, and I think that it's just a relation between equally, let's say, things on the same level. So let's say you do a state preparation and then a measurement, and then the measurement statistics doesn't fit into the prediction. Then you would just say, this just means that the state that you thought was the correct state has to be revised. That's how I understand the Cubist approach, that whatever measurement data you get, you adapt the prior. but you would not adapt the axiom that the Born rule is from.
Or actually adapt
Well,
the description of the
I
measurement
mean, you can.
rather than the preparation.
Yes.
I mean, it's-
Yes.
Are we discovering new physics from within quantum mechanics, or do you just like do empirical stuff?
No,
invent it. You know.
I think you always have
cubism,
this issue in the construction of any scientific theory. You know, there's
I think this
the
is
old the
general issue.
Duhem-Quine objections, or
I
whatever.
mean, it applies to the falsification of quantum theory in general, not specific to cubism.
But I think it has to do a little bit with psychology, right? So you're. No, I'm serious. I think you make a statement. So you take the Born rule to be axiomatic. You say, well, sure, if I come across data that falsifies it, I'm free to change my axiom. But do we really do that, right? So there's a little bit of a cognitive bias in everyone, right? That we have our viewpoint, and we're going to, if we've chosen that as our axiom, we're more likely to see outcomes of data color our views in favor of that axiom.
It's never obvious an axiom has been violated. You have to like do a lot of
Yes.
stuff, and eventually you say, you know what, this is not good enough. I'm going to change it.
Well, even
Yeah,
then,
if
often we don't give up theories which have many anomalies until we have a better idea that everyone agrees on.
Yeah.
But I mean, this again is a general issue in the philosophy of science.
It's nothing particular at all.
It's nothing particular to cubism.
No, it's not. It's not. Yeah, absolutely.
Yeah.
So actually, one could take cubism and take out the subjective Bayesianism and get something. I'm surprised many times that the way I do quantum mechanics is kind of close to that. Although I'm let's say a frequentist of sorts at least. So I think the basic view of probability is actually secondary. That would be my view, right? So as soon as you have a fundamentally probabilistic theory that this is your basic structure, then there are many subjective things that have to be done. For example, you have to say what counts as a repetition of the same experiment. The Bayesians definitely have to have that. Otherwise, you couldn't count empirical evidence collected towards correcting your prior, right? So you need the same kind of identification of what is the same experiment. It's the same fundamental primitive that you need in order to talk about repeated experiments. So on that level, it's very close, right? So your favorite interpretation of probability actually can be exchanged without exchanging all that much in the outlook of the theory. Of course, they would always say assigning a quantum state as a statement about my willing to bet something. Okay, but there's a frequentist statement that is very close to that. As soon as statistics is sufficient, that is, you have a good statistical basis for, let's say, a state tomography, then the Bayesian is bound to be a frequentist anyway, right? This converges to the relative frequency. So then we agree, everybody's happy. In situations where the statistical basis is very weak, then I would say, okay, if I don't know, I don't know. Right? But then the subjectivist could at least say, well, but I can make a guess. Scientifically, the difference between these two is also almost zero, right? Because these guesses are just irrelevant until they are backed up by
I
evidence.
think what you always ignore is is that you're right. In an actual practical situation, maybe you and I would basically do the same thing, though you call yourself a frequentist and I call myself a Bayesian. But what you really want to ignore is that taking a stance one way or the other molds how you understand or how you think about some of the potential quantum mechanical paradoxes. So for instance, if you have adopted a view that quantum probabilities are just, I shouldn't say just, quantum probabilities are degrees of belief, then you have an immediately natural explanation for why when I perform a measurement here, I update the quantum state over here without any implication of any kind of signal going across.
Good, that's obvious anyhow.
But
that's just the nature of correlation. Jesus Christ!
If it is somehow that my action here has changed a physical property over here, the propensity, the objective propensity for this object to give a certain outcome. Okay, maybe you can take that point of view, but the move toward the radical Bayesian direction was to say, I don't have to make a contrived story about how a signal was sent from here to there.
I totally agree.
So that the physical, objective, factive propensity has changed. So
that's
the work it's doing for you is conceptual.
Okay,
that's why the emphasis.
But
that's why I make
not
the
having
emphasis
to make contrived stories about correlations in terms of collapses is something that is definitely part of my setup. So yes, totally agree on that point.
And furthermore,
but that has nothing to do with
the conceptual
subjectivism.
changes also shape where you will look for ontological. Maybe you don't like looking for ontological statements, but I do think that Cubism is pushing in a certain direction for ontological statements in the end. But the way it does that is first by clearing out all of the things that are not ontological. And so if you can get a clear understanding of what things are not going to be in the ontology, then you've made progress. So for instance, you could say, oh, quantum states are not in the ontology, unitary operations are not in the ontology. At least we can eliminate these two, and that'll help us focus. So it does conceptually.
Again, complete agreement.
Okay.
Yeah.
I don't want to. We are actually over time, so I don't want
to.
Go home. So what I'll do is I will give. Is there anybody on the panel who would like to have a last comment on anything?
You do that.
Sorry.
You have the last word.
Well, I'm not going to. Well, I'm going to say a few things that aren't part of this discussion. But is there anything anybody wants to add before we conclude? Okay. So then what I would like to do is first of all thank everybody who came here. I think this tradition of having some kind of foundations meeting around the APS meeting is a good one. I hope we are able to continue it. And thank you for all coming to talk about such a apparently esoteric topic that nonetheless we believe is very important. So thanks for doing that.